Chapter 19, Entropy and the second law of thermodynamics, samples. Sample. The cyclic diagram A, B, C, D, A of a diesel engine is shown in the figure, where A, B, C, D are adiabatic process. BC is a constant pressure process, and the DA is a constant volume process. There's N more of working materials inside. Show that the efficiency of the engine epsilon equal to 1 minus TD minus TA over gamma times TC over TB. This is what we want to prove. Okay? Now, the efficiency by definition equal to the work done over the heat input to the system. And this work done equal to QH minus QL by energy conservation. So this is equal to, we have to calculate this one. Let's see this. Adiabatic process AB and CD. Then we show the QAB and QCD is 0. Let's see the constant pressure program. Okay. There's QBC because the constant, so equal to NCP delta T. Find out TC minus initial TB. Okay. Yeah. Because you look at this one, VC is larger than VB. The same P is constant, so T is proportional to V. V larger, T larger. So we get TC is larger than TB. So this number is positive number. TC larger than TB. QBC is the larger number. You have heat get into the system. Okay, and then so this was the Q high. And let's see another constant volume. In this process, W equal to 0, right? So Q equal to NCV T final A minus T initial D. Okay, and we see, look at this one, same V, PA is smaller than PD. And also the same V, P proportional to V. PA is smaller, so TA is smaller. So TA is smaller than TD. This term is minus number. And then this is called a Q low. Release this one. Okay? Okay, we write this one. Q high is from this one. Okay, QCP1. Q low is from here. Okay? It's equal to NCVTA over TD. That's the first we have. Okay? Then from here you get efficient. This is equal to T high over T low over T high. We put one inside, we get an answer. Okay? We can have another way to do it. This epsilon could work over TC. We find the works, we find TH, and we can get it. Okay? So as before, Q high equal to NBC equal to NCP TC over TB. Okay, and we want to find the W. The W is the whole cyclic whole cycle equal to AB work BC plus work CD plus work DA, and we will find this one. Okay, this AB, this is an adiabatic process. So Q equal to 0. By the first law of thermodynamics, W equal to minus E delta E. And delta E internal equal to NCV TB over TA by definition. Okay. And then we see, because this is adiabatic, it's okay. So W equal to minus DC. And WBC, BC, this is a constant pressure, so equal to P delta V, P VC over VB. Because W equal to PD. This is P is constant, taken out, so P delta V. Okay. P delta V. And PV equal to nRT. So we replace PV equal to nRTC. PVB with the nRPV. Okay. Anyway, PB equal to PC. But this one, this is the quantum volume. So it's W dA is 0. And this adiabatic, something like AB equal to minus CV TD minus TC. Okay. So this is W equal to sum of these two. Okay. What is the W equal to sum of these two? For these two, you get this one, you have R, TC, CVR, CP, okay, becomes CP minus, okay, CP. And the TB, here minus TB, okay, so CV, TC is the R. So you get NCP, TC minus TB, and NCV, TB over TA. We put this inside, put this one inside, we get the answer. Sample. A gasoline internal combustion engine can be approximately by the circle shown in the figure. At this one you have two adiabatic process, two constant volume process. Okay. Assume that an ideal gas used compression ratio of 4:1. That's when V4 is equal to 4 V1. And P2 equal to 3 P1. This is a given. Determine the pressure and the temperature of each of the vertex points of PV diagram in terms of P1, T1. Now, 1, 2, 3, 4. I want to find P, V, T. Okay? And the ratio of specific heat of the gas. I want to find the ratio of specific heat of gas. What is the efficiency of the cycle? Now we see this one. First we find P2. P2 is 3 P1 given. Okay. P1, V2 is equal to V1. So we get T. Okay? Yeah. Because P2, V2, T2 equal to P1 because V1. Okay? So then we find this T2 equal to 3 T1. Then question 3. PV gamma equal to P3 V3 gamma. This is adiabatic formula. Okay? So we know V3 equal to 4 V2 is given. Then we find this is 4 V2, okay, and this is, let me see, okay, P2 equal to 3 P1, okay, yeah. So in this case, V1 gamma cancel out, we get P3 equal to 3 P1. This is 3 P1, okay, over 4 gamma. And then we find the T3. P3 V3 over T3 equal to P1 V1 T1. We know P3 equal to this. V3 is 4 V1, so we get the T3 is 3 T1 over 4 gamma minus 1. Then minus 4. This is another adiabatic process. So P1 V1 gamma equal to P4 V1 gamma. Okay? We know this V4 is 4 V1. So we get a P4. P4 equal to 1 over 4 gamma. Once we get a P, we get a V, we get a T. P4 V4 over T4 equal to P1 V1 over V1. We get a T4 equal to T1 over 4 gamma. Then we get the first part. Every point 1, 2, 3, 4, we get a P, V, T. We will use this formula later. Since T1 is smaller than T2, why? Because this is a constant volume. So P is proportional to T. T is proportional to P. Now, P2 is 3P1. So T2 is 3T1. And T4 is smaller than T3. So we get the heat. Okay, heat in this process. Okay, the temperature is going up. So you have heat point get into the system. So Q12 is larger than 0 because temperature increase. And here, T4 is minus than T3, so you have energy going out. Okay, T34 is smaller than 1. This is heat get out. And these two programs, adiabatics, no heat exchange. We know that, so the epsilon equal to Q high minus Q low over Q high. Okay, now we find this one. Okay, Q, this is N2 is constant volume, so equal to NCV T2 minus T2. We know T2 is 3T1, so we put equal to this one, 2T1. And Q34 is out the negative number, equal to T4 minus T3. T4 is less than T3, okay? And then we put the T3, T4 inside, we get this one. And then we put Q, the pieces inside, and we get the answer. We get the answer. Now, we do another one. We use this definition, epsilon equal W over Q high. We know T1 smaller than T2, T4 smaller than 1, we know this one. So Q12 larger than 0 because the temperature increase, you have heat inside. And this one, your temperature decrease, you had heat go out, right? As before. And we did these two are equal to 0. So we find QH equal to Q. This is a QH here. This is a constant volume, so equal to NCV T2 minus T1 equal to this one. And omega W, we will find equal to this one, okay? And W over Q, we get efficiency, 1 minus 4 times K. Next page, we prove this one, okay? Now with that, W12 work is 0 because constant volume, you don't have a work dV, okay? And W23, this is adiabatic, equal to Q equal to 0. By the first law of thermodynamics, W equal to minus E delta, E internal, 2,3. This one equal to delta E, 2,3 equal to NCV T3 minus T2. And 3,4 is 0 because V is constant. And 4,1, similar like this one, okay, equal to NCV T1 minus T4, final initial, okay? And then we put them together. That together is minus NCV T3 minus T2 minus NCV T1 over T2, okay? And then this is the answer. We should T3 is this one, T2 is 3T1, T1 and the T4 is this one. We calculated before. So we get this answer. And this answer is the one we just used, okay? Sample. 1 kilogram of water in standard condition T, 0 degree of Celsius, P 1.13 times 10 to the 5th Pascal is 1 atmosphere, is brought to contact with a heat source of temperature 100 degree of Celsius, and is totally turned into water vapor. Find entropy changes of the water of source and of the total system. Question 2. If the water is brought to contact with a heat source of temperature 50 degrees Celsius first, after reached to equilibrium, it is then brought to a heat source of temperature 100 degrees Celsius and totally turned into water vapor as before. Find the total change of the entropy. Let's see water. Water has undergone two processes. There's water from 0 to 100 degrees Celsius. And the second is at 100 degrees Celsius from liquid water to gas water, vapor. Okay. First, we'll calculate the water from 0 to T. So its change of entropy is dq over T. Okay. The T is changed into the integration from initial to final. And dq, we can see, is mc dl dt. This is by the conducting law. Okay. And mc is constant, we take it out. Integration dt over t from initial to t final. And this integration is log. So we get mc log t final over t initial. This is a water from 1 degree to 100 degree. Then we have water, I think we put this number inside. This is 1.1473. These two have to use the Kelvin. This is 100 degree of Celsius, put 273. This is Kelvin. This is Kelvin. And we get this number, okay? This is a change entropy when water from 0 degrees Celsius to 100 degrees Celsius in water situation. And next, we have liquid water turned to water vapor at 100 degrees of Celsius. Okay. Delta S2. In this case, the temperature is constant. 100 degrees Celsius, 373 degrees Kelvin. 373 Kelvin. This is a constant to get out. Okay, so we get a T final and Q. This Q you could do ml. We put the number inside, we get 6 point. So altogether, the entropy change of water from 0 degrees water to 100 degree water vapor is equal to these two. Delta S1 plus delta S2. We put it 1 equals 6.355 10 to 3 joule per Kelvin. Next, we see the source. The source is always constant. Okay, integration for initial is always constant. 773 Kelvin. We take it out. Okay, so that's the Q. This Q including two parts. One is supply the water, let its temperature from 0 to 100. Second, supply to the liquid water, let its phase change to 100 liquid water. So we get a two part. One is MC F final minus FT. It's minus because it offer, it goes out of source. And the phase heat, ML. Okay? And we put on the main side, we get a number. Then we put everything together. Delta S total equal to delta water plus delta source. Okay, and we find this is last one minus 7.4. This is 0.0184 times 10. This is much larger than 0. If it is smaller than 0, there's something wrong with your calculation, right? Yeah. So let's see a second question. We put the reservoir 50 degrees first, and after it reaches the equilibrium, you put in contact in the reservoir 100. and the phase, and all water change to 100 degree water vapor. So the entropy change of water is the same. Let's see the source. We have two sources. One is 50 degree. We take this out, and this delta Q is MC 50 minus 0. Okay, this is minus because for a source it's output. Okay, and second source is 100 degree of reservoir, and this Q is from 100 to 50 is output. Also plus phase energy, M, phase heat, ML. We get this one. Then we put everything together. 1, 2, 3. Okay? And we find it's 0.077. It's larger than 0 at the second law of thermodynamics.